In this video, we're going to be looking at another way of dealing with inhomogeneities in the field through a trick known as the spin echo. Let's go back to first principles for a moment. Remember that oscillating transverse magnetic field has the effect of causing the nuclear magnetization to move from its equilibrium position pointing along the magnetic field to being precessing at some particular angle. And the most favoured angle for maximum signal is to have that magnetization lying in the transverse plane. How do we get just the right amount of turning? Well, we have to apply the oscillating magnetic field for just the right amount of time. And that time produces what is known as a 90-degree pulse. So let's go and look at how this 90-degree pulse idea relates to our earlier free induction decay experiment. There's the free induction decay, or FID, and the period of time here goes from 0 to about 2 seconds. So the 90-degree pulse happened right at the start, and the duration of that pulse was about 1 millisecond. That was the time needed to turn those nuclear magnetization vectors through exactly the desired angle of 90 degrees. Of course, that free induction decay is obtained with a nice homogeneous magnetic field. It's a long decay producing a narrow spectrum. The shim coils that we use to produce that very homogeneous field could also be used to make the field less homogeneous. By putting the wrong current through these coils, we could make for a much shorter free induction decay. And in order to demonstrate the spin echo trick, which I'm going to show you in a moment, it turns out to be very helpful to do that. So I'm just going to adjust the currents here and run this again. Pre-polarizing pulse, 90-degree pulse, and a very rapid free induction decay under this now quite inhomogeneous field produced by having the wrong currents in the gradient coils. And there you see a very broad spectrum now, and of course quite noisy because the height is reduced to conserve the total area of the spectrum. Let's just remind ourselves of the mechanism that caused this rapid decay when we had an inhomogeneous magnetic field. Remember then that spins in different positions of the magnetic field will have quite different Larmor precession frequencies. So that as time goes on, because of their different precession frequencies, they'll get out of step with each other and the total magnetization vector will decay away. It's rather like runners in a race. We've got some that are fast and some that are slow. And what we'd really like to do is to produce a handicapping when the fast runners go to the back and the slow runners go to the front. Let's just watch how we might do that. I'll start again with the spins in the inhomogeneous field, with some precessing faster and some precessing slower. They gradually spread out with time, but at some point we turn them over so that eventually they all come back into step with each other. What have we done there? We put the fast spins at the back and the slow spins at the front, so that when we perform that handicapping at an equal time later, they've all come back into step with each other. That's a perfect handicapping, and that's the spin echo trick. So what have we done here? We've turned the magnetization vectors through 180 degrees. And how do we do that? We use the oscillating transverse magnetic field. But instead of applying that oscillating field for the time required to turn through 90 degrees, we apply it for twice as long to produce a 180-degree pulse. So instead of the pulse being 1 millisecond long, the 180-degree pulse is 2 milliseconds long. This idea of refocusing is a bit like a time reversal process. The spin echo was discovered by Irwin Hahn, a young graduate student working at the University of Illinois in the 1950s. And that time reversal process that lies at the heart of the spin echo turns out to be one of the most important tools in magnetic resonance. So now we're going to carry out the spin echo experiment on the Terra Nova apparatus. We have to start with a 90-degree pulse, we wait for the magnetization to decay away, and then we apply the 180-degree pulse. And we're going to do this experiment using the fairly inhomogeneous magnetic field we have at the moment that causes quite a rapid decay. Let me run the experiment. What we're going to see displayed is the signal obtained after the 180-degree pulse. So what we see in the centre is the formation of the echo. Here, the spins processing at different frequencies are coming back into step to produce a maximum signal, and then they pass through with the fast ones at the front and the slow ones at the back again, getting out of phase again. On the right, as always, we have the spectrum. Quite a broad spectrum because it's quite a rapid decay. Of course, the complete spin echo experiment involved first a 90-degree pulse, a wait for a period of time for the spins to get out of phase, the 180-degree pulse, a wait for a further period of time for them to come back into step again. And what I'm going to show you now is the complete experiment. Here at the beginning was that 1 millisecond long 90-degree pulse. Here we see the dephasing due to the somewhat inhomogeneous magnetic field. No signal as we advance in time, but here at this point we have the 180-degree pulse. So from this point on, the spins are starting to get back in step with each other. And here, as the echo starts to form, we see them coming back into phase, perfectly in phase, at the top of the echo, passing through and then getting out of step again as the echo dies away. The total time here from the beginning of the experiment through to the centre of the echo is about 0.6 of a second. So the 180-degree pulse occurred at the midpoint at 0.3 of a second. There's always an equal period of time in this time reversal process between the 90-degree pulse and the 180-degree pulse, and the 180-degree pulse and the centre of the echo. So there it is, we made an echo. The question is, could we do this trick again? Could we apply another 180-degree pulse and have another echo, and another echo, and another echo, in a sort of endless train of echoes? The answer is we can. And that effect was discovered by Carr and Purcell in the early 1950s, and hence it's known as the Carr-Purcell experiment. So here's the single echo experiment. Now let's run the multiple echo experiment with multiple 180-degree pulses, all equally spaced in time. Prepolarizing pulse to start with, then the train of pulses to give us the multiple echo result. And here you see echo upon echo running across in time. These little gaps here are because we have to turn off the receiver during the transmit phase of the 180-degree pulse in order to protect the receiver. But in between, we pick up a signal, and in each case we see an echo. But there's something very obvious we notice about those echoes. Their amplitude is dying away with time. What's going on here? There's some irreversible process that's not enabling us to get a perfect refocusing of the magnetization. There's a random process here which is disturbing our ability to rephase the spins. And this is known as T2 relaxation. It's a stochastic process associated with the motions of the molecules. And it's a fundamental limitation to the length of time over which we can produce this time reversal effect. It turns out that T2 relaxation is really extremely useful because it tells us a great deal about the nature of the molecular environment and the dynamics of the molecules with which we're performing nuclear magnetic resonance. Let's go back again to our single echo experiment and see if we can see this T2 process at work. Here's the original FID, and there's the echo. And if you look very carefully, you can see that the echo amplitude is just a bit smaller than the original amplitude of the FID. So this ratio between these two tells us something about the rate of decay. You might wonder then, what's causing this initial decay here? Well, we know that's caused by inhomogeneity of the magnetic field. The T2 relaxation is a residual, irreversible effect even when we've tried to compensate for inhomogeneities in the magnetic field. And what's the name we give to this decay here to distinguish it from T2? It's called T2 star. Now, with all this talk of T2, you might have wondered, whatever happened to T1? Well, there is a relaxation process known as T1, and it relates to the return of the atomic nuclei back into thermal equilibrium. And in the next video, we're going to be looking at T1 and T2 and how we measure them.